This video traces the mechanical conversion of my CNC mill. The mechanical conversion of the mill used a kit from Precsion Matthews and is a pretty straightforward build. The original plan was to source individual components, build the adapters and convert the mill from scratch. To that end, I spent several months disassembling the mill, measuring all components and building a full model in Fusion 360. The mill teardown video shows removal of the manual operation components prior to this conversion. The Fusion 360 plans will be made available to anyone who would like to leverage my CAD work to pursue a bottom-up conversion path instead. It's been quite a while since the mill was delivered, pretty much the middle of the pandemic. The entire project had several major delays, but the mill was pretty much everything I could have hoped for. This is checking the run out on the spindle before things got interesting with the teardown. And as you can see, I had 2 to 3/10ths of a thousandth of an inch of run out. A great start for my high precision goals. Things to watch out for though are issues like paint build-up on machined surfaces, and in my case it looked as though this was from paint touch-up before delivery. The ways were definitely ground and showed signs of being scraped, but it was pretty minimal. It definitely allowed better oil retention on the ground surfaces, but I doubt that the precision was improved very much. This is actually the version 1 kit. Several improvements have been made for the version 2 kit, and it appears that the high precision kit now has a cheaper alternative. The ball screws in the kit have a diameter of 16mm with a 5mm lead, which means for every revolution, the screw will move 5mm. The precision on the ball screws is C5 grade, and they use double ball nuts to eliminate backlash. As you can see in this chart from THK, the C5 grade of ball screws are the first of the non-rolled ball screws and have an accuracy of 18 microns over a thread length of 300mm. This is the Y-axis subset of the print assembly. Note that the parts explosion shows the ball screw and nut separated. Do not remove the nut from the screw. Dozens of little ball bearings will escape from the bearing race. This image shows how the ball bearings may be recycled through a ball nut to provide continuous action. So let's start with the Y-axis ball screw coupler. The front of the ball screw rotates between two bearings, either side of a mounting plate fixed to the front of the mill base. When assembled in the mill base, the coupler is bolted to the Y-axis carriage. Next is the X-axis assembly. The length of the X-axis ball screw means that it needs to be supported at both ends. So, starting with the X-axis ball screw, ball nuts and coupler. The coupler is then bolted to the Y-axis carriage. The X-axis table is placed on the Y-axis carriage. Then the ball screw is attached to a plate in conjunction with two bearings on the left end of the table. A plate is bolted to the right end of the table where a NEMA 23 motor will later be fitted, which will support the right hand end of the ball screw. Finally, a cover is attached to the left end of the table to protect the bearings and ball screw. Next is the Z-axis ball screw. The only complaint I might have of this kit is that I would have used a larger diameter ball screw on the Z-axis. The weight of the milling head and the higher torque of the NEMA 34 Z-axis motor put a lot of strain on the ball screw. To account for some of this strain, the Z-axis incorporates thrust bearings rather than the simple bearing races used on the X and Y axes. We are again going to start by assembling the ball screw and the Z-axis coupler. The Z-axis ball screw and coupler are bolted to the base plate for the milling head. And then, the motor mount is secured to the top of the column, and the motor mount and thrust bearings are coupled to the ball screw. The Z-axis plate is a lot bigger, as it has to support a NEMA 34 motor as well, and this is where the two thrust bearings are going to be used. Thrust bearings are designed to be inserted in one direction to resist axial loading and thrust. A pair of them resist actual thrust from the Z-axis in two directions. However, you must have the two of them mirrored, with the writing facing in towards each other to be effective. The inset diagram is there to ensure that you get the thrust bearing orientation correct. The thrust bearings are pressed into the motor mount. It's an interference fit, and in this case really only requires moderate pressure, so a bench vise is all you'll need. The collars on all of the axes need to have some preload applied before the set screws are tightened. This may need to be tweaked later when the mill is being tested, as we will see in a later video. The last step is in placing a cover over the hole left when the manual controls at the top of the mill were replaced. Thanks for joining me on this mechanical build video. Future videos will look at the electronics build and control box layout.